Okay, so the subject of this lecture today D-branes. So D-branes are fundamental objects in string theory. These are derived from one-dimensionally extended string. You can derive these concepts, but they play a very important role in many constructions in string theory, and their properties have been explored over the last 30 years or so. And so there are a lot of things that we can tell. One important property of D-branes is that these are charged with respect to Ramond-Ramond gauge field. So this is something we discussed toward the end of the last lecture. So let me briefly recap that. So you have D-branes, and these are charged with respect to the Ramond-Ramond gauge field. Okay, so I pointed out the last lecture that if you consider type 2 string, then in the NS sector, you have graviton, you have antisymmetric tensor field, and then you have zeraton. Okay, so this B nu is rank 2 generalization of the gauge field. So just like the ordinary gauge field A have this gauge transformation, and in fact it's a Weinberg theorem that if you have massless spin-1 particle, it must come from gauge symmetry in order for the S matrix to be consistent. Similarly, this B field is not an invariant dynamical variable, but it transforms inhomogeneously under gauge transformation. So therefore, the invariant object, the physical observable, is actually the unsymmetrization of derivative of B, or you can write H is equal to dB in the form notation. So you can think of B to be rank 2 gauge potential. And then H is a rank 3 gauge field strength. So this is observable in string theory. Okay? So this is in the NS sector, which exists in type 2 string theory. Type 1, if you have open boundary condition, we will discuss boundary condition on the worksheet later, but then some of the degrees of freedom can be removed. Okay, but there are two types of type 2 string, type 2A and type 2B. And they differ by the chiral projection, or the way the GSO projection works in Ramond sector. So they differ in Ramond sector. Okay. So the ground state of Ramond sector is a spinor. So the ground state would be a bispinor. And then in the type 2A theory, they have opposite chirality, whereas type 2B theory, they have same chirality. So they have opposite chirality, and they have the same chirality. Now, if you have a pair of spinor indices, by using the standard groups algebra, the representation theory of Lorentz group, by using the standard representation theory of Lorentz group, you can show that both the pair of spinor, both with opposite chirality and same chirality, is equivalent to, can be decomposed into sum of antisymmetric tensors. But the rank of the tensors are different. So in the case of type 2A, the ground state of Ramond-Ramond sector is a bispinor with opposite chirality, and this corresponds to massless particles. So you can say that ground state of Ramond-Ramond sector is a massless bispinor with opposite chirality, but this is equivalent to the bunch of antisymmetric tensor fields. And so those correspond to so even rank tensors. And the equation, and on the other hand, type 2A, type 2B case, they are of the same chirality. And then by the standard Lorentz algebra, you can show that they are related to odd etc. Okay? Now, but there are two properties of these spinors that we have to understand. One is that the ground state for Ramond-Ramond sector corresponds to spinor that satisfies the Dirac equation. So that means that you have d slash alpha beta s beta gamma is equal to 0. For example, in the Ramond sector. In the type 2A, it is like that. And then in 2B, you have equation like that. And then you also have d slash alpha dot beta dot s gamma beta dot is equal to 0. And then d slash alpha dot beta dot s gamma, beta is equal to 0. So for each ground state satisfies two first order differential equations. Okay? So, and then you see that these Dirac operators don't mix dotted and undotted spinor indices. And the reason, and this is exactly why we can decompose spinor into chiral part and antichiral part. If the Dirac operator mixes chiral and antichiral one, then you cannot consider, it's not reasonable to consider chiral operator. On the other hand, mass term mixes the chiral and antichiral. And that's why if you have mass, then you cannot have chiral projection. It's something you should have learned in the standard model of particle physics. But these are, the point I wanted to make is that these are linear equations. So therefore, if you consider, if you decompose this bispinor into sum of antisymmetric tensor, then they should also satisfy two linear first order differential equations. And these are actually dc is equal to 0 and d star c is equal to 0. And similarly, this is equal to 0, and then this is equal to 0. These are exactly like Maxwell equations. So C satisfies the equation similar to Maxwell equation, and in fact also to this equation. So namely that here H satisfies this equation, and this is actually Bianchi identity. And the other equation is this. Okay, so this is the rank 2 generalization of the Maxwell equation. And then C field satisfies rank n generalization of the Maxwell equation. Okay? So this in particular means that there is some antisymmetric tensor such that C is equal to dA. So this really means that this Ramond-Ramond ground state should be regarded as field strength of some higher rank gauge. So that means that Ramond-Ramond ground state are field strength of A, mu, rho, etc. So gauge field. Okay, so this is what this means. There is another important property of Ramond-Ramond state of type 2A and type 2B, which is that these are chiral. Right? So this is I defined the ground state to be chiral. And so that means that in particular, if you define gamma 11 as gamma 0, gamma 1, all the way to gamma 9, and then it should satisfy the gamma 11 acting on the S should be either plus or minus S. And depending on type 2A or type 2B, so gamma can act on the one of the alpha or gamma beta, and depending on the 2A or 2B, the relative sign for the way that gamma matrix acts on the spinors are different. Basically, what this means, well, the fact that we are using chiral basis means that gamma matrix, if you decompose that into alpha index and alpha dot index, takes this form. Right. So if it is 2A, then one of the spinor index should have minus eigenvalue, the other should have plus eigenvalue, and like that. But you have this relation. So this translates into, because S and C are linearly related to each other. So C is a linear combination of S, while S is a linear combination of C. So that means that this relation we should be able to interpret in the language of C. And it's not hard to interpret it because the hint is that gamma 11 is essentially asymmetric combination, mu1, mu2, etc., mu10, gamma mu1, gamma mu10. Okay? So therefore, gamma 11 is the product of gamma matrices contracted with epsilon. Okay? And the way that you can read of this is that you start with gamma product of gamma matrix, and then contract that with bispinor. Say, for example, in the case of 2B, it's like that. Okay, and the reason that in 2B case you have to have odd number of gamma is that you need odd number of gamma in order to have chiral indices. Okay, so anyways, it's like that. So then it's very simple algebra that you can just do it in 5 minutes or maybe 2 minutes, depending on how good you are. That if S is an eigenstate of gamma 11, and if S is gamma is a product of gamma 11 is a product of gamma with epsilon, then you can easily see that this relation basically just means that C is equal to plus or minus star C. The sum of these things. So namely that there is a duality between C's. So this in particular means, for example, here you have mu nu rho sigma kappa delta, etc., and then you have mu nu rho sigma kappa delta epsilon, etc. And then so there is a duality between them. So let's see how it works. So for example, these are dual to each other. And so 1, 2, 3, 4, 5, 6, 7. So these are dual to each other. And then there is another one waiting here, which is dual to each other. And then this is self-dual. Okay? So that's what this means. So therefore, the ground state of Ramond sector satisfying Dirac equation means that in fact the ground state is an unsymmetric tensor field strengths coming from gauge field. These are Bianchi identity, and then these are equation motion for the gauge field. And then the fact that the ground states are chiral implies the self-duality of these field strengths. Okay, so that's what it is. Okay, so this is nice. We have a nice geometric interpretation, and so string theory suggests that there is a vast generalization of the concept of gauge symmetry. But there has been some puzzle about the existence of this higher form gauge field. And one of the puzzles have been the following, that in quantum gravity, we expect all that there are charged objects for all gauge fields. So this is called a completeness hypothesis. So this is paired with another idea that in quantum gravity there is no global symmetry. So I might actually talk more about that later if we have time. But so when we talk about symmetry of physical system, there are actually two types of symmetries. So one is a global symmetry. So this is actually, when we talk about symmetry, this is a genuine type of symmetry. That if you have global symmetry in quantum system, then there is a unitary operator that implements that symmetry, and then it acts non-trivially on the Hilbert space. Okay, so that's a global symmetry. And you can use Noether's theorem to construct a symmetry generator of this global symmetry. Gauge symmetry is of different type. So this actually does not act, this symmetry acts trivially on the Hilbert space. And these are mostly introduced for the sake of description of physical system in the Lagrangian formulation. And so you might think this is a fake symmetry. So for example, example of that is U1 gauge symmetry in Maxwell's theory. So in U1 gauge symmetry in Maxwell's theory, then you have local gauge symmetry. So in some sense, there are infinitely many symmetries because you can do gauge transformation at each point differently, right? And under that, gauge field transforms. But gauge field transforms just like I wrote over here, inhomogeneously. And then the physical observer is actually field strength. Those are electric and magnetic field. And these are invariant under gauge transformation. Okay. So therefore, gauge symmetry itself does not act non-trivially on the Hilbert space. There is actually a remnant of gauge transformation that acts non-trivially on Hilbert space. So for example, you can, so any gauge symmetry that are in some sense normalizable, that it only changes gauge field configuration locally, does not act non-trivially on gauge field, on the Hilbert space. But there is what's called the global gauge transformation, which changes the boundary condition at infinity. And that can act non-trivially on Hilbert space depending on your setup. And this actually is the definition of electric charge. So we say electric charge is conserved. So that means that the electric charge, there must be an operator electric charge which acts non-trivially on Hilbert space and commute with Hamiltonian. This sounds puzzling because gauge symmetry is supposed to not act on the Hilbert space. And the reason for that is that what we call electric charge corresponds to gauge symmetry that changes the boundary condition for quantization of the Maxwell theory. Okay. So there is some subtlety to that. But what I wanted to say is that there is an important distinction between these two types of symmetry. You have global symmetry and you have gauge symmetry. And so when we talk about symmetry, it's important to understand which kind of symmetry we are talking about. And there are different properties. And if you introduce gravitational degrees of freedom, they behave differently. First of all, in quantum gravity, global symmetry is actually forbidden. And there is a long-standing conjecture starting from John Wheeler in the 60s, maybe late 50s. And in the case of ADS, in the context of ADS CFT correspondence, actually you can prove this. And it's a theorem in ADS CFT. I might talk about that later. So that means that if you have low energy theory that seems to have gauge symmetry, as a global symmetry. So for example, standard model of particle physics has global symmetry. It's called baryon number minus lepton number is an exact symmetry of a standard model of particle physics. And but if you assume that, if you expect that there is no global symmetry in quantum gravity, that would mean that this baryon number minus lepton number symmetry must be either violated by some effect in the ground unification or some higher energies, more fundamental theory, or in fact this can be a gauge symmetry. So there might be some gauge field that we don't know yet, which exists in the ground unified model but not in standard model, for example. And therefore, what seems like global symmetry is actually gauge symmetry in this case. Just like what's electric conservation of electric charge is not a global symmetry, but it's actually gauge symmetry in this case. So those are the possibilities. Gauge symmetry behaves differently. In the gauge symmetry, you expect that whenever you have gauge symmetry, there must be some degrees of freedom which are charged, and which carry non-trivial charge with respect to gauge symmetry. And there is a argument for this, lots of different arguments for this. And in fact, again, in the context of ADS-CFT correspondence, you can prove this. So it's actually a theorem in ADS-CFT correspondence. In fact, there's a stronger statement one could make, which is that very often when you have gauge symmetry, there's a dual gauge symmetry. So just like in Maxwell theory, you have electric charge, but there is also magnetic charge. So both are conserved. So if you assume that there is a charged object for both of them, then there's a Dirac quantization condition. So that means that the electric and magnetic charge has to satisfy certain quantization condition, and they only exist in some kind of lattice. In that context, the completeness hypothesis implies that all possible charges allowed by Dirac quantization condition should be populated. Okay, so this is the hypothesis. Now, the reason that I'm bringing up this general consideration of quantum gravity is that this would require, if you assume this principle of quantum gravity, then we would expect that there are some charged objects with respect to this Ramond-Ramond wave field. So are there charged objects with respect to the Ramond-Ramond gauge field? Okay, so that's the question, and so I'd like to answer that question. So first let's see what kind of things that we should expect. So for example, in type 2A, so C even rank. So that means that C, if you write C is equal to dA, then A can be 1 form, or 3 form, or 5 form, etc. So similarly, type 2B, C odd rank. So therefore, if you write C to be dA, then A can be scalar, or unsymmetric 2 form, or 4 form, etc. Okay? So there's a bunch of those things. And so what kind of things are charged with respect to these? So that's the kind of question. Okay? One form is easy to visualize. So if you have one form, then if you have one form, then there can be a particle. There must be a particle, charged particle. And then if that charged particle moves in space-time, then there is a corresponding phase factor, exponential of IE integral of gauge field along this path, gamma, or C. Or C is used here, so maybe gamma. But gamma I don't want to use because I use gamma matrices a lot, but let's call it gamma. So this is a standard, like what you run in even electromagnetism, right? And so this is a natural thing to do. But you have higher rank tensor. So that means that there must be some kind of extended object. That the charged object must be extended. So therefore, if there are charged objects with respect to Ramond-Ramond field, the string theory must contain lots of these extended objects. So there's a question of what these are. So that's one question. So the question number one is what are the extended objects? By extended, I mean that the higher dimensional world volume with a higher dimensional world volume objects. Okay. If it is rank 1 tensor gauge field, it can be a point particle. If it is rank 2, it can be string. But there are lots of higher form gauge fields, so that means there are lots of higher dimensional objects in theory. So, is it a nice concept? So that's one question. The second question that there cannot be fundamental string. So that's another problem. So there cannot be fundamental string. And of course, these are closely related. If there are charged object, it has to be extended object. But you can directly see that the fundamental object cannot carry charge. So how do you see that? Well, so suppose you have fundamental string coming in, propagating, and then suppose that you want a situation where it emits some Ramond-Ramond field. So can you do this? Well, so in order to calculate this amplitude, we need to calculate some fundamental string F1 and then F2. So there are some physical state for fundamental string F1 and F2. And then there must be some kind of vertex operator or some operator here which emit Ramond-Ramond grams. So there must be an amplitude like that. Okay. But this is problematic because this contradicts with the property of the Walsh's theory. So this is in Ramond-Ramond Grant state. So left movers are chiral fermions and right movers are chiral fermions. So even though Ramond-Ramond Grant state itself is a boson in space-time, but from the Walsh's computation, it's actually a product of fermions. And so you cannot have, so the problem of this is that therefore you can think of, you can think of this as some kind of combination of left moving fermion operator and right moving fermion operator. And we are interested in calculating charge. So that means that F1 and F2 should be of similar kind of state, right? Because we are looking for charge. So for example, if F1 is the NS sector, F2 should be also NS sector. So that means that this amplitude involves odd number of left fermion and odd number of right fermions. And so therefore, you cannot have such amplitude. And you can actually directly see that you cannot write down such vertex operator. So this is in contrast with NS sector. So in the NS sector, you have this H, which is dV. So this is NS2 form. And so in that case, you can actually calculate this. Okay. In fact, there are some explicit examples that you can calculate. For example, you can have here the graviton, and you can have here H, and then you can have here H. So you can have bilinear of H going to graviton, and this is certainly allowed because if you have NS field propagating in space-time, then it can carry energy and momentum, and that can be detected by graviton, and then by flipping it, you can see that this 3-point function should be non-zero. So you can have this to be non-zero. So that means that there must be a charge, the fundamental string can be charged with respect to the NS2 form. And in fact, you can easily write down such coupling, because if you have worldsheet, which I denote by gamma, then you can have we can have a process of coupling this B field to the worldsheet like this, and this is allowed coupling, and in fact this is what we have, and so NS2 form gauge field is coupled, the charge with respect to B field is carried by string worldsheet, and this is exactly what we expect, because B field is twofold, and so naturally coupled to two-dimensional object, and that's the worldsheet of string. But then for each one of these, you have some extended object, and so you can ask what these are. So interestingly, for example, type 2B string, for example, have unsymmetric rank 2 gauge potential in the Ramond sector. So that means that type 2B should have another string, for example. So in addition to fundamental string, type 2B series should have another string. So there are two types of string. And in fact, type 2B string is, as we will see later, known to have self-duality properties. And the self-duality exchanges these two types of string. Okay. So that was a puzzle. So where are these fundamental objects? Okay. So of course we need to look for them. And so suppose we didn't know about D-branes, and we'll see later that D-branes carries these charges. But that was a very, very non-trivial discovery. So this was discovered by Joe Porchinski. The idea of D-brane existed before, but he was the one who actually realized that D-brane carries Ramond-Ramond charges, and this was like a very fundamental discovery. And but this was a highly non-trivial discovery, so we cannot immediately jump on it. So we'll do more pedestrian approach. So if somebody asks, well, how do you construct objects which are charged with respect to this gauge field? How do you do that? Well, so one immediate idea that one can think of is to find some solution to low energy effective theory. So in low energy, so one idea is to find a solution or solutions to the low energy effective theory theories of the type 2A and 2B string theory, and study their properties. So that's one approach one could take. So the low energy effective theories of type 2A and type 2B theory are type 2A or 2B supergravity. So it consists of gravity, the metric G mu nu, and then this unsymmetric tensor field, and the dilaton, and then bunch of Ramond gauge field. And plus fermions. So we look for solutions to this equation. Okay. So Ramond-Ramond gauge field have let's call this so for example in type 2A, as I said, there are C, nu, etc. So let's call this, and then type 2B, we have C mu, rho, sigma, etc. And so let's call this collectively as C P plus 2, where P are some integers. And so P plus 2 is a rank of this gauge potential. So the why plus 2? So this is the reason that there's a reason that you have to it's natural to add 2. The reason is that you have this two-step process. So you write C P plus 2. By solving Bianchi identity, you write it in terms of extended derivative of gauge potential. So the gauge potential will be rank P plus 1. So if you have rank P plus 1 object, then there must be some kind of P plus 1 dimensional space for which you can integrate this P plus 1, right? And then this gives you a coupling of this A to this P plus 1 dimensional object. So the natural object that's coupled to the Ramond-Ramond gauge potential with rank P plus 2 is a P plus 1 dimensional object, which you can think of as P dimensional, the world volume of the P dimensional object. So supposing that you have P dimensional object, and then you move in space-time, and then it sweeps out P plus 1 dimensional world volume. Right? And so this is that P. This is that P. So supposing you have P dimensional object. So just like string is one dimensional object, point particle is zero dimensional object. Suppose you have P dimensional object, and that P dimensional object propagates in space-time, it sweeps out P plus 1 dimensional subspace in space-time, of which there is a natural coupling of this P plus 1 for gauge potential, and from that you can derive P plus 2 dimensional form, and those are the Ramond graphs.
So that here, like a P could be -1 and -2.
Yeah, I wrote P in integer.
Yeah.
Okay, all right. So what is the action? So the relevant part of the action is 2 pi to the 7, the string length, which is related to the tension of string. So it's a 10-dimensional action. And you have a dilaton, and then you have the rich tensor for the metric. And then 8 minus P factorial 2 and C P plus 2 squared. Okay. There are other terms, but for example, there are the P goes for all even number or odd number, depending on whether you are in type 2A or type 2B. But let's just focus on the single Ramond-Ramond form to look for object charge with respect to this P plus 2. Okay. So you have this Ramond form, and I'm also setting timing of the B field, because I'm interested in object not charged with respect to B field, which we already know to be string, but we are interested in object charged with respect to this Ramond-Ramond. So we consider coupling, we consider restrict the action, truncate the action, to the Einstein-Hilbert action, the kinetic term for Dilaton, and this. There is this exponential factor here of Dilaton, which is natural, because Dilaton is related to the string coupling constant. So one of the purpose of life of string theory is that the Dilaton gives you string coupling. Let me tell you a little bit about some subtlety in low energy effective theory of string. So the Dilaton expectation value sets the string coupling constant. So which I denote as L string is equal to exponential of phi. Okay, so it's natural that S, we can write S as 2 pi 7 LS 8 and then GS square. And then you start with Einstein-Hilbert action. So one natural way of writing this is in this way, where you have this combination, LS square, the GS square, LS to the 8. And this is actually the 8th power of Planck constant, Planck length. And then this is also proportional to the 10-dimensional Newton coupling. Okay, so Newton coupling, so if you look at the Einstein-Hilbert action, the Einstein-Hilbert term is multiplied by inverse of Newton coupling constant. And then in 10 dimension, Newton coupling constant is 8th power of Planck length, which is related to each Planck length in 10 dimension is proportional to LS and a 4th power of the string coupling constant. So this is probably the more natural way of writing it. But then we wrote it in this way because this string coupling is set by the Dilaton expectation value. So there's actually a non-linear term like that. So the way that you write the Einstein-Hilbert action in this way is called the string frame. So there is a Dilaton and metric. So if you have quantum field theory or field theory, you have to decide what kind of parameterization you make for fields. So here I have chosen the normalization of the metric so that the Einstein-Hilbert term looks like this. And this is the natural way of writing low energy effective action from the point perspective of string theory. So for example, if you use this metric, then the worldsheet action of string in 2 dimensions is written in this way, without any extra factor of Dilaton. So this G mu couples naturally through the string worldsheet. But it's unnatural from the low energy point of view of low energy effective action because you have this exponential coupling to Dilaton. So for example, when general relativity expert solves the Einstein equation, you don't have this funny scalar field going around. So you can get rid of this by multiplying some exponential. Now it depends on the coefficient, depends on the dimension of the metric. So if you rescale the metric by some certain power of exponential of phi, then with respect to this tilde, the low energy effective action can be written without the exponential factor of Dilaton. So this is called Einstein frame. So this is called Einstein frame because with respect to this G tilde, Einstein-Hilbert action takes the standard form. So So when you look at the string theory literature and look for solution to low energy effective theory, it's important to know in which frame you are calculating. Of course, if you know one, you can easily translate it to another, and so it's not a big deal, but it's important thing to know. And so depending on your purpose. So if you are interested in understanding it from string perspective, then it's natural to use string frame. But from the point of view of general relativity, it might be more natural to rescale. So anyway, so this is the convention. So for today, I'm going to work in string frame. Okay, so that's why I wrote this action in this way. Okay, so let's try to look for why am I doing it? So the reason I'm doing it is look for objects. So can we? So the question is that here is a question. The question is that can we construct solutions to this theory, which is e to the minus 2 phi r plus kinetic term plus Cp plus 2 square that are charged with respect to Cp plus 2. Okay, so that's the question. Oh, by the way, so there's another interesting feature, which is that here I said that it's natural that you multiply exponential of minus 2 phi, because this is equal to 1 over g string square. And it's natural that classical kinetic term is multiplied by 1 over g string square. But you see that for Ramond-Ramond field strings, there is no 1 over g string square multiplied to it. And this is another peculiar feature of Ramond-Ramond ground state. That if you actually walk through the counting of string coupling constant multiplied to string amplitude, then you can actually show that in Ramond-Ramond sectors there is no string coupling constant multiplied to. And so from that, when you write down low energy effective action, you don't have this Dirac coupling over here. So that's the reason. So anyway, so this is what we want to do. So we start from this low energy effective action, which I wrote over here, and then you write down Einstein equation motion for Dirac, and equation motion for antisymmetric tensor field, and then try to construct a solution which carries charges. So what does it mean that it carries charges? Well, so this is the definition. So what means? What does it mean? What does it mean to find an object that carries a charge? My handwriting is getting worse. Not quite legible, I'm afraid. So let me do it again. So what does it mean to have an object that carries a charge with respect to its Ramond-Ramond field? Okay. So let's try to remember in the case of electromagnetism. So in the case of electromagnetism, you have this charged particle, and then there is a trajectory gamma, and then there is a coupling, like that, right? So this is one way of doing it, but there is another way of thinking about it. So this is a space-time picture, but supposing, for example, so this is R, say 1, 3, but let's look at the spatial section. Then there is a point particle, and of course it's extended in time direction. And then you have a sphere. You have two spheres surrounding it. And then you integrate the electric field in the normal direction over S2. And then this gives you electric charge. Right? So this is the definition. You can, if you like, this is the definition of electric charge. Now, well, we can also write this in a more fancy way. We can also write it in a more fancy way. We can also write it in a more fancy way as S2 of integral of star of F, where F is the field strength. Right? And if you have magnetic field, instead of F star, you integrate F. Okay, so this is, you can think of this as a technique. So you can also do that in 1, 3. So the reason that you can integrate F star is that in 4 dimensions, so F is 2 form. In 4 dimensions, F star is 2 form too. And point particle in R3 can be surrounded by 2 surfaces, so you can integrate it. So what are the general situations? So suppose you're in 10 dimensions, so 1, 9. So you have a P form. You have P plus 2 Ramond-Ramond potential. So now you have P-dimensional object. And then it's extended in the P plus 1 dimension. Okay, so from that perspective of R9, you have a P-dimensional extended object. Okay, so this is a particular point. So it's a P-dimensional object. So you want to surround it by something. So what is the dimension of this? What is the dimension of this? So you can surround this by a sphere. Okay, so what is S? What? S? What? So it should be 8 minus P, right? Is this not right? Yeah, I think it's 8 minus P, right? Because if you add P, so it must be like codimension P plus 1. So P plus S minus P is 8. Right? So you have P dimension in this direction, SP minus 1, and then there's the extra dimension which is radius. They add up to 9. So that means that if you have P plus 1 dimensional world volume in 10 dimensional spacetime, you can surround that by 8 minus P dimensional sphere. So you look for something that integrates over SP minus 2, and sure enough, that's the dual of P plus 2. Right? Because if you have Hodge dual of n form, it's in 10 dimensions, it's 10 minus n. But here n is P plus 2. So that means that the star of Cp plus 2 is 8 minus P form. So you can naturally integrate this. So this is actually the Ramond-Ramond charge and so you can write this as n. I think my normalization is n, so let me double check. Yeah. So I normalize this to be n, and n is the Ramond-Ramond charge. Okay, so therefore the question is that can you find a solution to supergravity which is extended in P plus 1 dimension, so that if you surround the transverse direction, the direction transverse to this P plus 1 dimensional space, it gives rise to this. Okay, so that's the solution. So we have to choose also the answer for the metric. So the answer for the metric I choose is the following thing. So I'm going to just choose simplest setup. So what I'm going to do is write the metric so that but it's basically flat along the world volume direction and maybe curved in the direction transverse to it. So this is so in 10-dimensional metric is equal to flat 10 minus 8 p direction plus e to the rho, which is some function along this p direction. Okay, so this is a solution that respects the symmetry. Okay, so you can look for a solution of this type. Okay, so let me just write down the actual solution because the process of looking for a solution of this type is a very well-known technique in GR. So these are basically generalization of Reissner-Norton solution. So these are generalization. So in general relativity, for example, if you have a charged particle charged with respect to electric and magnetic charge, there is a famous Reissner-Norton solution. It's one of the very few exact solutions to Einstein equation known. So that's for the point particle, and you just extend that to p plus one dimensional thing. And so you can write down the solution, and in string frame, it is given as ds squared is equal. So you have two functions, just like in Reissner-Norton case. Rho f plus rho dt squared plus square root of f minus of rho summation I is equal to p dxi dxj dxi, and then the rho is a transverse coordinate, f minus of rho minus 1/2 minus 7 minus p 5 minus p f plus of rho d rho square. So rho is the coordinate transverse to the world volume of the brain, and then you have rho square f minus of rho 1/2 minus 7 minus p 5 minus p, and then the sphere coordinate. So this sphere is this sphere that wraps around. So the notation is that you have this p-dimensional object extended in time direction. So the coordinate in that direction is xi. The coordinate transverse to this is rho, and then the sphere surrounding it is omega. Okay, so those are this notation. Okay, and so this is metric. The Dirac term is given by string coupling square times. Okay, so it's actually useful to just write it in this way. Is equal to f minus of rho of minus p minus 3 over 2. Okay, so lots of formulas, but you see that these are essentially given by these two functions, f plus and f minus. And f plus and minus are not difficult functions. 1 minus r plus minus over rho to the 7 minus p. Okay, and rho plus minus, this is in GR, you know, there are often Reissner-Norton solution has two horizons. Right? And so these are inner horizon and outer horizon. This is a generalization of this notion. And the rho and the r plus minus parameterizes the mass and charges. So the mass m is given by 8 minus p, r plus of 7 minus p minus R minus of 7 minus P. So essentially like that, divided by some numerical constant, 7 minus P 2 pi to the 7, and then there is some kind of dimension dependent constant, and then LP to the 8. The detail you don't have to worry about. The important thing is that you have this dependence, and the charge N is given by R plus R minus of 7 minus P divided by some number. So let me just transcribe that over here because it's getting a bit crowded here. And yeah, and since these are important. So the point, you don't have to understand this notation too much detail. I just wanted to show that there is actually rather the explicit solution to Einstein equation expressed in terms of elementary functions, and so those solutions exist. Okay, and moreover, that there is a horizon. So as far as R plus is greater than R minus, there are no negative singularity in this metric. So these are as good as the standard rational Norton solution. So let me write down once again the formula. So the mass, so in a clean sheet of a blackboard. So mass is given by 8 minus P R plus the 7 minus P minus R minus of 7 minus P. Remember that the P is related to the rank of Ramond-Ramond field. The normalization factor is 7 minus P 2 pi to the 7 dP LP to the 8. LP is 10-dimensional, it's defined over there, it's 10-dimensional Planck length. And dP is just some number, 2 to the 5 minus P, pi to the 5 minus P over 2, and gamma of 7 minus P over 2. Okay, so you can see that there might be something funny happens at P equals 7, but this 0 actually cancels this 4. So it's okay. And the charge is given by R plus R minus 7 minus P divided by dP, string coupling, and LP of LS of 7 minus P. Okay. So the solution has no negative singularity. If R plus is greater than R minus. And this translates into the equality that mass is greater than n divided by 2 pi to the p gs and s to the p plus 1. So this is actually p-dimensional generalization of rational Norton bound. So you know that in general relativity, so this is a generalization. Of rational Norton bound. That if you have a charged black hole solution, the black hole charge with respect to the standard Maxwell field, the electric field, then there must be an inequality between mass and charge. This probably you should probably want to write it as absolute value in case charge is negative. in order for the solution to have no negative singularity. And so the mass should be greater than charge with appropriate normalization. So this is a higher dimensional generalization of this inequality. In GR, in rational solution, there are various intuitive understanding of why such inequality exists. One argument that we often hear is that, for example, if this is opposite, you cannot make them. So for example, suppose so how do you make a charged black hole? Well, you try to sort of combine objects with charge and masses, and then you try to gather them, and then eventually, if the mass is sufficiently large, it collapses into black hole. Right? So that's but if the objects are charged, and in order to create an object which has non-trivial charge, you have to combine objects with the same charges, right? The same charge repel each other by Coulomb force. So if you have, for example, two objects of mass m1, charge e1, and mass m2 and charge e2, each of them are not heavy enough to make black hole, so you want to combine them to make black hole. So the mass m1 and m2 attract each other, but charge e1 and e2 repel each other if they are of the same sign. If they are of opposite sign, then you don't want to do that because that will reduce the charge. So if you want to have as large charge as possible, you want to combine same charge object. But they repel each other. If this inequality is violated, you cannot construct such thing because Coulomb force, basically this proportionality constant is based on so the Coulomb force is of course proportional to the product of charges. Newton force is proportional to the product of masses, and the relative normalization of these forces, Newton force and Coulomb force, is given by this normalization. So this basically says that you cannot, if this inequality is violated, you cannot make this in the standard way. So naked singularity is sort of nature's way of telling you that you shouldn't even try it. And so basically there is this inequality. But often something interesting happens in the limit when r plus goes to r minus, which mass hits this one. So in that case, you have barely some kind of naked singularity. So typically in the rational Nordstrom solution, what happens is that so you have this horizon, and then the naked singularity. And so r plus approaches r minus, the naked singularity approaches to the horizon, like that. And so it's sort of naked singularity is very hidden. So you might say, well, the equality should somehow be allowed. And in fact, something interesting, very interesting happens near the horizon in that limit, as we will see. Okay, so anyway, so that is so extremal black hole solution is the limit when r plus goes to r minus. Okay, so this is sort of interesting. So the supergravity therefore has such solutions. So these are studied by people like Horowitz and Strominger in the early 1990s, okay, before the deep learning. So and so there are lots of objects evidently in gravitational theory which are extended in p dimension space, and therefore world volume is p plus 1 dimension, and these are carrying the Ramond-Ramond form. So these are termed as p-branes. Okay, this is named by Paul Townsend. He's a British, but he has this funny British humor. So I guess this is a pun, right? So there is a term called p-branes, which is about somebody who has very little intelligence, and so these are. I think that's how he came up with this name. Kind of interesting sense of humor. But anyway, so you have these p-brane solutions. And the extremal limit of p-branes are particularly interesting for a variety of reasons. So in the limit for p r plus goes to r minus, the m goes to capital the absolute value of n divided by 2 pi. So the p gs it is p plus 1. So this is the lightest p-branes. It's the lightest p-brane for the charge n. Okay. So p-brane is supposed to have low intelligence, but this one has even the lowest intelligence for given charge. And so this must have some interesting properties. And in fact, you can show that in supergravity, this preserves some fraction of supersymmetry. Okay, and the fact that it should satisfy some fraction of supersymmetry can be seen in the following fact. So I wrote down this rather funny-looking metric, and but there is actually an interesting thing about this metric, and one of the interesting features, which I hope we can extract from this, is that so suppose I set plus and minus to be equal to each other. So then these two functions are the same. So this gets simplified actually. This should get simplified, and one important simplification is that okay. So this goes this way. Right? One important simplification is that this factor and this factor becomes the same. Right? This factor and this factor become same, and then this gets simplified. But importantly, this factor and this factor becomes the same. And this means that actually the Lorentz symmetry of the world volume gets restored. So here the time component of the metric and space component of the matrix are different. And it is related to the fact that in general this is the excited state. This corresponds to the excited state of the brain. But if you set R plus goes to R minus, then F plus becomes F minus. If R plus is equal to R minus, then F plus is equal to F minus. And the metric gets simplified, and then in fact the metric becomes the square root of F plus rho and minus dt square plus summation of I is equal to P. 1 plus p dxi plus f plus of minus 3 half minus 7 minus p 5 minus p d rho square plus rho square f plus of 1 half minus 5 minus p 7 minus p of d omega 8 minus p squared. So you have Lorentz invariance here, and supersymmetry is a square. If you have supersymmetry, if you square it, you get Lorentz symmetry. So having Lorentz symmetry is a prerequisite to have supersymmetry. So you see that restoration of Lorentz symmetry has to do with preservation of some fraction of supersymmetry. Okay. So this is nice. This suggests that we have nice. We would expect a nice description of a p-brane solution in its extremal limit when the mass you have the p brane has smallest mass for given tension. Okay. Well, I said I keep calling it as mass, but in fact it's an extended object, so you should really think of this as a tension, namely the energy per unit volume of the p brane. Okay. But there are two problems with this. So one problem is that there is a negative singularity in general. When p equals 3, actually there is no negative singularity. So p equals 3 is a particularly nice situation. And we'll see one of the nice features plays an important role in ADS CFT correspondence later in this course. And so, but that's one problem. So therefore, I manipulated this supergravity solution as if it makes sense as a smooth solution, but in fact there is a negative singularity in the solution. Okay? I did that just to exhibit Lorentz symmetry, but this actually there is a problem, strictly speaking, to make sense because there is a negative singularity. So that's one problem. And another problem is that string theory in this space-time is difficult to understand because target space is curved. It's a curved space-time. So if you try to understand it from string worship point of view, it's a non-trivial interacting quantum field theory in 2 dimensions. You cannot take, so there is no obvious symmetry besides the simple Lorentz symmetry. So you cannot expect to have a nice sort of solution or some dynamical understanding of worship theory. So that's another obstruction. So we need some alternative description. So that is given by p brane. Okay, so it turns out that there is actually a beautiful alternative description of this situation, not in terms of supergravity, but actually in string theory in flat space-time, but with another object that carries the Ramond-Ramond charge. And so in the next lecture, I introduce the notion of d brane and show that this actually is alternative description of the same thing, namely that you have actually a description of the same charged object, but are more suitable in describing that in the context of string theory. So that will be the next lecture.